Howdy, folks. Welcome to CS128 Honors. Today is another lecture on messaging. First, let's do a couple of reviews. So, first, conceptually, they are sets of code that can run in parallel to each other. And in Rust, each thread is associated with a function or closure. Both could be referred to as threads. When we launch a Rust program, the main thread is created by default. And we can also create additional threads using the function thread colon spawn. Now, our threads must never take or capture references. The values must always be owned. So if our thread is a named function, the function input must be an owned value. And if it is a closure, we must use a move keyword to force a move of ownership, or a copy or a clone must be a copy of captured data into the closure. In the last lecture, we also looked at the MPSC pattern, the multiple producers, single sender pattern. In this pattern, we have multiple senders of data, that is multiple producers, and a single receiver of those data, that is our single consumer. An example of that we talked about is our mailbox, where we can have multiple senders of mail, that is our multiple producers, and the mailbox is a single place where you will receive the mail. So it is the single consumer of mail. We can achieve MPSC in Rust using the structs MPSC colon sender and MPSC colon receiver. They are the address and the mailbox that we will use. And an instance of these structs will be created when you call the function MPSC colon channel. This opens up a communication channel and creates the address as the mailbox we see. We can use a method sender.send to send a message using our address, and the method receiver.receive to receive a message from our mailbox. Remember that the receive function is a blocking function. That means that it blocks the current thread until a value is received. Now, as we see that the function channel creates a single sender and a single receiver. But aren't we supposed to have multiple producers? Like, in other words, we should be able to send messages to a same receiver from multiple senders, right? Well, we can do that. The solution is to just give everyone a copy of our address so they can send to the mailbox. How do we do that? Well, the sender struct is clonable. That means that you can clone the sender, and these new senders will send to the same receiver as the original. So what we can do to achieve MPSC between threads is to just clone the sender and move the new one to a new thread. A little note here is that throughout the lectures and assignments, we will often name the sender with the variable name tx for transmitter and receiver the variable name ix for receiver. Now, a little bit of how the receiver work. So as we mentioned, the receiver dot receive is a blocking function. That means it blocks the current thread. And there are two conditions where receiver dot receive will stop blocking. One is once it receives a message, then receiver dot receive will return an OK containing a value m, where m is our message. The second case is if all senders go out of scope. That means they are dropped. What happens what happens here is that, well, once all senders go out of scope, the receiver will receive no more messages since there are no more senders to send the messages. And also the function receiver or receive will return an error. So as opposed to OK when there's still senders. So the function receive will return error after all messages have received. So there are two conditions where this function return error. that both and both must be satisfied. The first is that all senders have gone out of scope, and the second is that all messages have been received. And here is an example where we create more, where we send multiple messages from a one thread by using a single sender and receiver. Here in the code, we create a transmitter that is a sender and a receiver. We move the transmitter into a new thread and we send messages after durations of 1 second. At the end of the thread, we see the TX ground scope. So we will, after this new thread end, we will no longer have a sender. In the main thread, we will repeatedly call the receive function until it returns an error. This basically what this groundlet syntax do. We will explain that later. So let's look at how this code actually works. So this is our code from the lecture slide. We spawn a new thread, move the sender into that thread, send a bunch of messages, and then in the main thread, we will keep receiving until the receive function returns an error. Let's try running that and see what happens. So as we see here, the main thread will print out the messages we receive from the other thread, from an hello from another thread, and then after it ends, after we receive all of them and this function returns an error, the program will end since the main thread will finish. We saw in that code that we use something called a while-let loop. So what exactly is it? Well, the method receiver.receive is just an example of a pattern we often encounter in Rust, where we constantly check a function while it returns okay, and we break the loop once it returns an error. The syntax is basically while-let pattern equal to expression and then our code. So this syntax allows you to loop while our expression matches our pattern. Note that unlike match statements, our pattern does not have to be exhaustive. In fact, it is only a single pattern. So say we have an enum, then our pattern is only a single variant. And this loop will break once our expression no longer matches pattern. And here's a concrete case where we do while-let OK value m equal to receiver or receive. This loop loops while the receive method returns OK. And we also see that our pattern is not exhaustive. We are only looking at the OK case. And this loop will break once the receive method returns an error. So you can kind of infer that from the loop. We only do while receive while I dot receive returns an OK. And here's an example of actually using MPSC by voice name. So here we try to send messages from multiple threads. So first we create a single sender and receiver using the channel function, and then we spawn a bunch of threads, and then we also clone the senders. Remember that each new clone of the original sender will send to the same receiver, and then we remove the sender clones into the thread, where from them we will send messages. From them we will send messages. And then we do the same thing as earlier, where in the main thread, we will keep checking the receiver while it returns okay, and just print out the messages. Let's look at how that code actually works. Right? This is a code from the lecture slides. Let's try running it and see what happens. All right. We see print out messages from every thread. So the message could be in the form message, number message from the from third number. But something weird is happening here. This program doesn't seem to end. It seems to be hung up somewhere, maybe by a blocking function. Well, the only blocking function that can be reasonably be called at the end of the main thread is the receive function. So the receive function must be blocking, but there's no new message. Why is that? So remember that there are two conditions for the receive method to return an error. All senders have gone out of scope, and we have received all messages. So in this case, we have received all our messages, right? And all the senders have also gone out of scope. I mean, all these new threads, we move the new senders into them, and once these threads end, the new senders will get dropped. But it looks like we still have a sender remaining. Well, which sender is that? It's our original sender. Note that the only senders getting dropped throughout this whole process are the cloned senders. Whereas the original sender is still there and it hasn't got dropped yet, which is why ice.receive is blocking the main thread instead of returning error. How do we ensure that TX got dropped? Well, we can just drop it manually by calling the drop function. And when we call this function, we drop the variable TX. In this case, it's the original sender. And this will ensure that the receive method on the receiver will return an error once every other sender in every other thread get dropped. Let's try running that again. And our program actually finishes now. This is because since we dropped the original sender, the receiver, the receive method will actually return an error once all these new senders get dropped. And this the correct code we saw earlier, where to ensure that our program actually finishes and ice.receive actually returns an error, we have to call dropped on TX. Remember here that we need to drop our own sender. Now, as we emphasize, the receive method returns an error when our senders go out of scope and all messages are received. And the transmitters are dropped when they go out of scope, or you can call dropped on them. Note that that's automatically called dropped when variables go out of scope, but here the function is still there, so that you can manually call it ahead of time if you wish to. In our case, we wish to drop the original sender ahead of time, and so we call dropped on it. When applying that to thread messaging, we can either manually drop the original copy of the transmitter. This is our preferred way of doing things. Or now we can also move the original copy of the into the last producer thread created, so that the original copy gets dropped when that last thread ends. But this may be harder to coordinate, and so the preferred solution is to just manually drop our original copy. Next, let's try to perform some real computation with the MPSC pattern. So here we have a collection of data of values from 0 to 10 times 10,000. And then we create a bunch of threads wherein for each thread, we will give them an own copy of a subset of the data. And the copy will be determined on chunk size and the number of the thread. And we also give them a copy of a clone of the sender. What each thread will do is that it will calculate the sum of its copy of of the data subset, and then send that sum as a message. In the main thread, we will receive the messages from the other threads and print them out, while also adding them together to get the overall sum. And then we print out that sum. So what this code is doing is that is just calculating the sum of the values from 0 to 10 times 10 times 10,000 using multiple threads to shorten the computation time. Let's look at how the code actually runs. And this is the code from the slide. Let's try running it. Well, here you see that, oh wait, also I forgot to print out I forgot to print out the overall sum. So let's try doing that again. So here's what I could print out. So the main thread will print out every single sum it got from the other thread, from the child threads. And then at the end, it prints out the total sum after receive every messages. So that means after receive method returns an error because all senders got dropped and all messages are received. And the sender got dropped because we dropped our own original sender using the drop function. And all the other sender clones are dropped when these new threads end. And here you see the sum for each subset of the data and the overall sum for the range from 0 to 100,000. Do note that we can also iterate through a receiver as if it was a collection. So the syntax looks like this for messages in X in receiver, curly braces, and outcode. This syntax will iterate through all incoming messages. So it's very similar to if you were iterating through a vector or an array. And it will also blocks between iterations when no new messages arrive yet. And this loop will end when the in force when the for the same conditions as when the ice.receive method returns an error. So this loop ends when when we have received all messages and all senders got dropped. This is basically a more succinct version of the while-let loop. And here's the example of the code from earlier, where instead of doing while-let, we just do for value in X. So for every message the third send to our receiver. And then this code will produce the same result as a while-let code. And that's it. That's everything about messaging. And the next lecture, we will explore share state in multi-threading.